Hey folks, I'm Brian Pane. I'm excited to be giving a talk for Rust Dublin on the 3rd of June about how to test unsafe Rust code. As more and more people use Rust to develop low-level software like operating systems or embedded systems, it starts to become inevitable that your most mission-critical Rust code will have to use some unsafe Rust features. And so I'll be talking about tools and techniques that you can use to help make sure that your unsafe Rust code runs safely and correctly. Thank you. Thanks for joining, everybody. I'm Brian, and I'm excited to talk today about techniques and strategies for determining whether your unsafe Rust code is indeed reliable. I'll talk about tools and techniques and some best practices for what to do when you're working with a code base that has unsafe code, meaning that the Rust compiler can't do all the checks and guarantees that you're used to in safe Rust. I got interested in this topic a couple of years ago when I started contributing to open source Rust projects. I was really excited about the whole Rust space because I had worked on a lot of C and C++ projects in past work and had spent way too many long nights debugging memory corruption, and really liked this mission that a lot of people in the community are taking on lately of let's make all our critical software infrastructure memory safe so that it can't have memory corruption or crashes or resulting security vulnerabilities. Was a mission that really resonated with me. And as I got more involved in the Rust ecosystem, I really liked what I learned. There's this compiler with a borrow checker that does all kinds of heavy lifting at build time in order to guarantee that your Rust code isn't going to experience memory corruption at runtime. Just brilliant stuff. Unless you use this unsafe keyword in Rust that basically declares that what follows is code that is impossible for the compiler to validate the soundness of at compile time. And as I contributed to more Rust open source projects and looked at the ecosystem of crates that they used, I found myself running into this unsafe keyword a lot more than I would have guessed. And it wasn't just me. The Rust Foundation did a study a couple of years ago and found that at that point about 1 in 5 public Rust crates on crates.io used some unsafe code, which was a higher number than I would have guessed. And when I saw this, I was initially puzzled, wondering, like, what's the deal here? Is this just an artifact of C programmers who picked up Rust and are not letting go of bad habits? Or is it people getting way carried away with aggressive performance optimizations, trying to take matters into their own hands when maybe they shouldn't? Well, not necessarily. Turns out that there are good reasons why smart people use unsafe code in their Rust projects. Maybe you've got a library in C that you need to use. Well, you have to write a bit of unsafe Rust to call it. Or maybe your Rust code itself is going to be a plugin to some existing system written in C++. You'll have to write some unsafe Rust to deal with the raw pointers that they want to pass you. Or maybe you need to use a bit of inline assembly language for some specialized functionality. Welcome to Unsafe Rust. Or maybe, and I've seen this increasingly common in a lot of Rust libraries, maybe you're doing something that moves around a lot of data, and so you want it to run as fast as possible, and you notice that the very latest and greatest CPUs have new features. AVX 512 in the x86 world is an example. It's a new set of extended instructions on the latest and greatest CPU models that can process much more data in parallel and give certain applications a huge speed up. But the previous decades worth of x86 CPUs don't have those newest instructions, and you want your code to be portable, and you don't want to have to ship many different versions of it for subtly different part numbers of different CPUs. And so you say, I'll use the Rust target feature mechanism to have the fancy new version of my code that uses the new processor features where available, and the fallback version that'll run on the older versions of the CPU, and I'll detect the right one and call the right code at runtime. which works great, except to do that, you have to use Unsafe Rust.
If you're exhausted before you even get to your desk, then check out tcube co-working space. Located at O'Connell Bridge in Dublin city centre, means a maximum walk of just 3 minutes from over 100 Dublin bus routes, Dart Station, and both Red and Green Lewis. And after a long day of code crunching, getting home or meeting friends for dinner is also a breeze. We offer a low-cost, no-frills model, which means you're not paying for free stuff that you'll never use. tcube offers a range of flexible daytime and 24/7 options, meaning you can join our community of freelance and remote software developers from as low as €277 per month. And that includes VAT, coffee, and 1 gigabit Wi-Fi. So if you're looking for a distraction-free workspace, which you can come to and then get out again to enjoy your life in the comfort of knowing that you've been at your most productive, then get in touch today for a free trial. Call us on 675-9777 or find out more online at tcubedublin.com.
And that creates a dilemma, because the places where you have to do those sorts of things I just described tend to be the really low-level critical code. You run into needs like that when you're writing an operating system, or you're writing networking code, or writing an encryption library, or building an embedded controller, which are basically the last places where you want memory corruption. Those are all the types of code that probably got you into writing Rust in the first place, because you had suffered the indignities of memory corruption in C++, and you wanted to avoid that with compile time checks, and suddenly you've got to use these bits of unsafe code where the compiler can't save you. So what do? Well, there's hope, because even if our code isn't necessarily safe, we can still make it sound. These are two important distinct concepts in Rust. Sound code is code that doesn't have undefined behavior. So what's undefined behavior? Rust has a long list of things, but they all basically are some form of doing bad things with memory at runtime, using memory that you've already freed, or freeing it twice, or I give you a slice with 10 bytes and you try to read the 11th byte of it. Things like that, as well as some things like arithmetic overflow. Safe Rust code is guaranteed by the compiler not to be able to do any of those bad things at runtime. Unsafe code is code where the compiler can't understand what you're doing well enough to guarantee one way or the other. Doesn't mean that your code is unsound, though. Just means that we're going to need some additional help to find out if it's sound or not. And that leads me to the topic of this. How do we deal with code that we hope is in this small slice of the Venn diagram, where we had to use some unsafe mechanisms for good technical reasons, but we want our code to be sound, to be reliable, to be free of corruption, free of security holes? So to set the stage, I brought along some Rust code with me. I've, for example, got a little Rust function here that'll write a given byte pattern to a buffer. You can tell it where the buffer starts and how big the buffer is, and it'll fill in the bytes. And I've got a C version of it too, because sometimes you end up using C or C++ libraries from your Rust. And of course, you can write a little extern C unsafe wrapper to enable us to call our C version from some Rust code. And let's write a little bit more code for my sample very bad examples library here. I've got a function that reads a buffer and computes a crude checksum function. Here too, you tell it where the buffer starts and how big the buffer is, and it'll iterate through and add it up. And of course, I've got a C version of that as well. And because I'm a conscientious developer, I'll write some test cases. Here in my first test case, I'm going to create a buffer on the stack, 5 bytes of data, and I'll then use my read function to read all 6 of those 5 bytes. This is unsafe, and it's also unsound. Undefined behavior at runtime. Next, I'll test out my C version of the buffer write function. I'll create a 5-byte buffer and write to all 6 of those 5 bytes. Also unsound. We can do some more things in our test cases here. I've got a bit of code that'll create an array on the stack, then let it go out of scope so it no longer exists, And then, thanks to the power of unsafe code, I can then read from it. This is very unsound, but it's a good thing I'm writing test cases. I can do the same thing on the heap. I can allocate a box in Rust, which creates some memory on the heap and initializes it, and then drop that so it gets uninitialized and freed back to the runtime. And then, because I slyly stored a pointer to it before I got rid of it, I can read from it or write to it. Extremely unsound. The challenge is, if we can do bad things like this using unsafe code, if we can do unsound things like this, how can we detect them? And most importantly, can we employ the aid of some software to help me detect the bad things in this code, to automate the process? There are a lot of permutations with these examples of things that I've done that are unsound. Reading a buffer, reading beyond the end of a slice, writing beyond the end of a slice, or using an object that's already been freed. And the object in question could be on the heap or on the stack, and I could be trying to access it in Rust code, or maybe in some C or C++ that I'm calling from Rust. Gives me a test matrix here of 12 unsound operations, and I've implemented all 12 of them for my example code base here. And because I'm a conscientious developer, I will run the tests. And it turns out that all my tests happened to pass due to nuanced implementation details. In a couple of cases, I slightly cheated for the sake of demonstration by putting adjacent buffers full of 0 bytes after some of these buffers, but I want to make the point here that this is a case where I've got thorough regression test coverage. I ran a coverage measurement analyzer, and it told me I have 100% test coverage on this little library, and all my tests passed. Now, is the code sound? No, of course not. It was intentionally unsound. So I need some more help. I need some tooling help to assist me in finding unsoundness in my Rust code. First place I'll start looking is static analysis tools. Static analysis has been a field of research in other programming languages for decades. The idea there is that you build some sophisticated software that you can point at your source code, and it'll read your code and understand it and reason about it and get back to you with reports of problems and say, here you're using memory that might have already been freed, or there you're walking off the end of an array, or things like that, all based on a static reading of the source code and a whole lot of data flow analysis. In recent years, people have started building tools like this for Rust. So I decided to check out a couple of them. One that looked really promising is called Rudra. It was built by a research team at Georgia Institute of Technology. They built their Rust static analyzer and pointed it at a whole bunch of mature open source Rust projects and ended up filing over 100 bugs for previously undetected soundness issues. So really great showing from this tool, demonstrating the power and the potential. Unfortunately, because it was a research project, they announced a couple of months ago that it's no longer maintained. I found an old snapshot on GitHub, but it wouldn't compile on my laptop, so I had to look elsewhere for potential tooling. There's another similar tool that AWS built in open source called Connie. It too is a static analyzer. You point it at your Rust code base and it tries to make sense of it and reason about the soundness of the unsafe parts of the code. The people who built it similarly pointed it at a lot of complicated Rust code, and they found, for example, previously unknown bugs in their Rust hypervisor and in some Rust networking libraries. So good stuff, really strong potential there. You do have to write some extra code in order to use this tool to guide the static analyzer to the parts of your code where you want it to prove specific things, but we can give it a try here. The integration of it into your code looks something like this. You write proof functions that look kind of like unit test functions that you'd be familiar with, except instead of a test directive at the top for Rust unit tests, they have this proof directive. And the key concept here is where you've got some inputs to your unsafe functions. You can initialize them with this Connie any expression, which tells the static analyzer, when reasoning about this code, assess what would happen for any possible value of this variable. What if it's 0? What if it's 1? What if it's slightly smaller than the size of the slice that I'm using it as an index into? What if it's slightly greater? What if it's infinity, or at least maximum int? Things like that. And so I wrote my proof functions like this to ask the Cane static analyzer to look at the unsafe functions in all 12 of my scenarios of unsoundness. And it found things. Here, for example, we can see it finding a pointer dereference can happen beyond the bounds of a slice because my code by definition isn't checking for array bounds when it's doing its references. And overall, it found all the intentional soundness problems in the Rust parts of my test code base. A known issue of it is that it doesn't analyze C or C++ that you're calling from Rust. And so it was unable to see the potential problems lurking in those parts of my intentionally unsound code base. But a pretty good showing from this new tool, and an example of the potential that's there with static analysis tools. This is a relatively new area for Rust, but I think it'll be one worth keeping an eye on because for good reasons people are finding it necessary to use unsafe blocks of code in Rust, and if some static tooling can find a lot of problems, it could really serve as a good safety net. But if these tools are in their early stages, maybe we should also look at dynamic analyzers, especially if we need a combination of Rust and C support in our code base. Dynamic analysis tools have been around for ages in the C and C++ world. They work in a couple of different ways, but the common theme is they'll take your test executable and run it in some sort of environment where they can scrutinize all the memory accesses and see if you're doing crazy things, reading something that you've just deleted, or allocating 5 bytes and reading the 6th of them, etc. Some of the dynamic analysis tools do this by running your code through a CPU emulator. Others tap into the compiler build system and produce a special version of your executable with additional runtime checks baked in. Either way, they tend to massively slow down the running of your tests. And because they're catching things during your unit test execution, by definition, they can only catch problems that your tests thought to create. But despite those drawbacks, these tools have a lot of history, have been a powerful approach in the C++ world, and they're widely available. So let's take a look at what's out there. Valgrind has been a go-to in the Linux world for C and C++ code for ages. It works by taking your Linux executable and running it under an emulated CPU, looking at the memory accesses and trying to catch bad things happening. You can run it for your Rust code as well by setting some arcane environment variables and then invoking cargo test. And Valgrind finds some stuff. Here, for example, in the C version of my buffer reading code that's called from Rust, Valgrind is able to say, hey, you are reading past the end of this object that you allocated on the heap, and that's going to cause some problems. Ran Valgrind for the whole test code base, and it essentially found everything, whether it was called from Rust code or from C called from Rust, everything involving the heap. Not so good with finding things on the stack. The reasons why involve nuances of it that other folks would be able to understand better than I, but my basic take on it is there's information that the compiler has at compile time about the boundaries between objects on the stack that may not necessarily be visible to Valgrind, whereas allocations on the heap it's got good visibility into because it can see when you called an allocation function. And so we've got a tool here whose superpower seems to be it can find things in your Rust code and things in C called from Rust, unfortunately for heap only. If you're using pure Rust, there's a newer tool called Miri that is a better alternative in some cases. Doesn't work for C called from Rust, but works really well for Rust. And the way Miri works is similar to Valgrind, except instead of trying to operate on your executable program as is, it meets the compiler halfway. It takes something called the intermediate representation. What's an intermediate representation? Well, when you're compiling with Rust C, which has LLVM as its backend code generator, at a point midway through the compilation process, your program exists as data structures called intermediate representation, which are not yet architecture-specific machine code, but are in a form that's much easier for machines to work with than source code. Kind of an interesting middle ground for something that wants to do soundness analysis on. And so what Miri does is it takes this intermediate snapshot of your code in a structured data form, runs it in a virtual machine, and looks at its memory accesses. And it too can be run with a handy cargo subcommand. And when we run it, it too finds things. In this example, it's finding a buffer overflow, in this case on the stack. Miri, I should note, is nicely programmer friendly. It told me where in the code the problem happened. Heck, it gave me a snapshot of the line of code and even underlined the particular bit of that line where the bad memory access happened, and then it showed me where the allocation of the memory in question had occurred. So very nice tool if you're using pure Rust, and it finds things on the stack and on the heap pretty reliably. Both Miri and Valgrind can be very effective with code bases that are well suited to their strengths. They both tend to run your test code really slowly. So one thing you can do is have lots of small unit test cases and rely on the cargo test runner to parallelize them. So how can we amplify our test coverage? Well, one technique that's become increasingly popular is fuzz testing. This is the practice of executing your code with random inputs to see what happens, which I recognize sounds slightly crazy. It's non-deterministic by its very nature, but in practice it tends to be a very powerful technique. Lots of projects that have adopted it have found that it's effective at uncovering subtle bugs in code that already had pretty good test coverage. To use it, you need to build some test scaffolding to generate random inputs of the appropriate data types and then call your code and evaluate the outputs. In Rust, there's a tool called Cargo Fuzz that you can install that does a fair bit of the heavy lifting for you. With Cargo Fuzz, you'll just have to do a bit of integration glue by writing functions like this that look a bit like unit test functions, except they're wrapped in this macro that says, Cargo Fuzz, please work on this bit of code. The key idea here is that you give the fuzz target macro arguments that tell it what data types you need it to generate random values of. In this case, I wanted to test with all different randomly generated sizes of how big my buffer read would be. And so I set a size as the parameter for the testing framework to randomize for me. I did this for all of my various buffer read and write implementations in my test suite, whether stack or heap, C or Rust, and give it a try, and fuzz testing found stuff. A couple of things are noteworthy here. One is it ran address sanitizer for me automatically as part of what it does, which is cool because if a problem happened but not badly enough to cause a crash, a SAN could still catch it. Another thing worth noting is that the output of this, while insightful, is also somewhat inscrutable. What specifically has this fuzz test found? It's found a bus error on some horrifically large hex number representing a program counter address, and it's given me a stack pointer and a base pointer as well. I assume that means something, but it's hard to tell what. A complication with the way the fuzz testing works is, as I've used it in this example code base, it might put such wildly out of range inputs into some of my code that it's trying to read the 1/1,000,000th byte of my 5-byte buffer. At that point, it's helpless to correlate the memory address where it got a segmentation fault with any object in the program because they are miles apart. So you sometimes find that, yeah, things went wrong, and you can get a backtrace to say where in the code it went wrong, but it's not quite as human-friendly as something like Miri in telling you with a carefully constructed test case exactly where the data in question was exhausted. But it did find things. I ran it on 8 of my soundness tests and it managed to catch them all. I didn't run it on the use after free cases because triggering that tends to be less a matter of calling with unlucky inputs and more a matter of just writing completely broken code. And so I tested it on the scenarios that depended more on the values of inputs. And fuzz testing in this simple example managed to be really effective at catching some things. So I've looked at a survey of a whole bunch of tools here. Admittedly, they all had some limitations. Some of them had incompatibilities, either with a code base or with the operating system I wanted to run on or the CPU. Many of them required writing extra code to tell a proof solver where to focus or to tell a test harness where to do some additional fuzz testing. Most of them ran pretty slowly due to the nature of what they were doing. Some of them, like the fuzz testing, are non-deterministic by their very nature. Some of them missed stuff, which is definitely a limitation. However, despite all these drawbacks, remember where we started. We started with my example of a test suite that had 100% test coverage, every single test passed, and it was full of broken, unsound code that could have resulted in memory corruption or crashes or security vulnerabilities if I had ever done those things in a production code base. And so there's a lot of power available here in tools like these if you add those to your development process. And so what would I recommend, given an ecosystem of different tools that have different overlapping strengths and weaknesses? I like a defense in depth approach of combine multiple layers of security, multiple layers of defense. First thing is start with a solid foundation. Having a good functional test suite with thorough coverage helps you get more power out of all of these soundness checking tools. Peer code review is also really powerful. Once you are certain that your unsafe code is perfect, then you hand it to your coworker and they tell you 10 things that are wrong with it.
Hi, it's Jerry Nolan here from Stack & Co. If you're stuck in your job, considering your next career move, or even just curious what the software engineering job market is like out there at the moment, reach out to me at Stack & Co. We'll have a confidential conversation, go over your career aspirations, your goals, and how to progress your career to get there. And if the timing is right for you, we can introduce you to some of the best software engineering career opportunities available in Ireland today. Reach out to me via our website, stackand.co.
Next, it's easy to integrate these tools, whether they're static analyzers or dynamic, into pretty much any project's continuous integration build pipeline. Chances are, if you're doing anything important enough that you ended up doing some unsafe code in there, you've got regression tests and you've got a build system, a CI system, and a pipeline. And so it's easy to add in additional steps to the pipeline to say, well, let's run the tests with a dynamic analyzer. And for the dynamic analyzer, Miri, it turns out, works extremely well. If you're doing pure Rust, very friendly and easy to work with. If you're using a combination of Rust with C or C++, Miri won't be able to see into the non-Rust code. That's where ASAN can be a powerful tool. ASAN, as we discussed earlier, can also be a powerful tool because you could use it for a production canary. Run some beta workload through it, see if it catches anything with production data that your test data didn't manage to trigger. Finally, fuzz testing is there. Non-deterministic, but in practice can be pretty darn powerful and is a really cheap way in terms of human effort to amplify the power of your test suite. And what I've observed is a lot of well-run open source Rust projects that need unsafe code doing a combination of these things, integrating multiple tools into their ecosystem so that they can ensure that their unsafe Rust code is still sound Rust code. And with that, thank you so much. questions, comments, ideas? Yeah.
I was just very curious that did you like pass your test code to like one of these AI tools like Claude or VS Code to see if they can find the problems or just
Yeah. Did I use an AI tool? No. Yeah.
it's just a test. Like does it determined by the text?
Yeah. I specifically wanted to see what was available in the ecosystem of tools purpose-built for this. I know people have gotten some good results, especially in recent months with LLM-based tools. For this study into unsafe code, I purposely decided to limit myself to mostly deterministic things and tooling dedicated to Rust testing. But LLMs can be another tool in your toolbox, and in the spirit of once you've got your foundations of you've got your test code, you've got your code base, you've got a continuous integration system, as you find new tools to add to your toolbox, you can plug them into that pipeline.
Yeah. So thank you for the presentation. I wanted to say that you mentioned that Kani is somehow a static analyzer.
Yeah.
I don't think so, because it is actually a bounded border checker.
Okay.
It's a formal verifier, basically.
Yes.
Up to a certain bound.
Yes.
Yeah. So basically, that's why using Kani. That's why you have the keyword proof.
Yes.
If you have that keyword, that means that you are using formal verification behind the scenes.
Yes. Exactly.
So that's why.
I'm being a bit loose with terminology, calling it a static analyzer, mostly to differentiate it from these dynamic tools that have to run your test code. But the key point is what it's essentially trying to do is prove the hypothesis of soundness in my function. And in order to do that, it's got to prove that for every possible input, there cannot be an undefined behavior.
Exactly. And there is another tool called VeriFast, with an I.
Okay.
That which is basically, let's say, an extension of Kani.
Okay.
And this tool is performing symbolic execution. And symbolic execution, basically, it's like a proof. It will simulate the different execution paths of your program against a specified property.
Nice.
So if the symbolic verification works, that means you have a proof that your system is completely sound.
Great.
But with Kani is basically DMC, so if you reach that bound, so basically you will not have a problem.
Right.
But it's a good tool to find counterexamples.
Exactly. Yeah, it ends up becoming a proof of a problem.
Exactly.
A demonstration of a problem rather than a guarantee of soundness.
And I just wanted also to add something related to LLMs and agents. I think they're quite extremely powerful to find bugs, because basically LLMs reason about programs deductively based on the shape of the program itself, and it can infer basically hidden patterns on the behavior. Okay? And as you said, as you mentioned, I think the way to confirm those potential bugs is by using, for example, formal verification.
Yes.
You take that bug and then try to translate it in a formal verification tool to confirm if it is actually a bug or not. Yeah.
Makes sense.
So that's why it's also a very, very good tool.
Cool, thanks.
It's kind of like interesting test you made there about the child frame allocating some bytes, and then that goes away to the calling frame, and then you use pointer to what was in the child frame. But we need to realize that stack is actually not going anywhere.
Right.
So technically, that frame, while the function is gone, this data is still valid. It's still in memory. It's still stack allocated for this thread. So you pass the pointer to completely valid memory that only logically is valid. Now, this is only true in a non-optimized build, especially in Rust. Rust doesn't even use stack properly. We use, I think from code code, I know it uses kind of region allocations.
Right.
The whole move semantics is about, I have a data structure here, I'm now moving those fields into different structure, different variables. There's nothing moving anywhere.
Right.
They stay in the same address. We just give them different names.
Right.
So if I say I move this field of the structure to a new variable x, that's just a language thing, just a
Yes.
semantics. Compiler will do absolutely nothing with it.
Right.
There is no need to copy any memory. So when these kind of things happen, you can't really put any guards and sentinels to say, oh, this is allocated, because obviously it was all optimized and we don't even, there is no even memory movement,
Right.
no instructions in assembly generated to actually work with it.
Exactly.
So the fact that you talked about, it was Miri that uses actually LLVM,
Yeah.
right? To actually, because when you use normal compiler and compiler, this is what you're gonna get. But if you use a tool that is using LLVM to actually understand the language
Right.
and decompose and produce the intermediate representation, that doesn't follow the same memory allocations, that doesn't follow the same kind of, there is no concept of a stack frame that can be wrong or right. There is, you can do proper analysis.
Yeah.
So I think like tool like Valgrind that you run on one binary wouldn't help you very much with the release version here.
Right.
But if you do actual analysis, or if you have a tool that actually understands and, as you say, does the symbolic analysis as well, then you can really capture those cases, because this doesn't get optimized. This doesn't get
Right.
You're looking at the semantics
Yeah.
and not the actual binary output.
Yeah.
So,
And it's at a point in the compiler where it understands lifetimes of things
Yeah.
much better than the resulting machine code which has no understanding of lifetime of anything.
Yeah.
Yeah.
Let's assume I don't use unsafe Rust,
Right.
but I have a lot of dependencies.
Yeah.
According to your data, it's 20% great with unsafe Rust. Even if my database does not use unsafe Rust, and I have pretty good code coverage in my unit test,
Right.
and still have to integrate something like fuzzy testing, because it's not hundreds, but maybe 5, 10 dependencies that depends on unsafe.
Right.
So all benefits of Rust becomes useless because I have to invest a lot in the testing. I cannot trust anymore.
No, you can trust Rust, but trusting an ecosystem of third-party packages you depend on is turning out to be a very complicated problem. And you just noted one. What if all my safe Rust code, where I've been very careful not to do anything that could possibly be unsound, what if it uses some other crate that uses some other crate that 6 degrees of freedom away from me has some unsound, unsafe code? That's one of many, many things that can go wrong in the transitive closure of the crates that I'm pulling in. There are many things that people are worrying about in the cargo ecosystem lately, things that have happened similarly in the NPM world for
Supply chain
Node.js. Is your software supply chain reliable? And I'm starting to see Rust projects taking different approaches to this. It's still an open problem where people are still developing their best practices. Some of the things I've seen, for example, are projects that know they are going to be used in other people's critical applications, getting really, really strict about not having dependencies of their own outside of test code. I've done PRs for projects where I pulled in a dependency on a new crate that was a reputable crate, but they said, no, we want to have a 0 external crate dependency guarantee and be at the bottom of a dependency tree, not in the middle. You can't always do that. For example, multi-layered dependency chains are sometimes inevitable. There are practices people are developing lately in terms of things like building delays into how soon they pick up a new point release of something after the code drops. That, I'll wait a day or 30 days or what have you. It ends up being a very wide-ranging problem space because unsoundness, unintentional unsoundness is just the tip of the iceberg. there have been enough attacks on especially open source software supply chains lately that you now have to worry about somebody having hacked a crate that is getting pulled into your code base. And it's not an unintentional memory corruption, it's intentional. And the good news is as the community and the ecosystem continues developing solutions and best practices for that case, those will also help with the unintentional issues of can I trust my software supply chain, in terms of we'll probably be seeing people develop ways of measuring and grading the risk or reputability, depending upon what it is that you're importing. If you can start to build reputation scores, for example, that okay, I know the company or the open source community that is building this particular crate is one that has rigorous software development processes, and I know how they test their stuff, then I can be aggressive about taking on new versions of code from their ecosystem. Versus if I don't know those things, then maybe I am much more cautious about integrating their stuff quickly or integrating it at all.
And that's assuming, of course, that somewhere along the line they don't start using crates from other places and
Right.
don't tell you that.
Right,
Yeah.
right. And that's why I imagine we'll start seeing providers of crates stating their policies on how they manage their own supply chain, where that becomes part of their trustworthiness, is what policies do they use to police their downstream. Yeah.
Generally speaking, we also saw a proposal to the Rust Foundation to have a better standard library, because Rust has an incredibly minimal standard library. So I believe SCDX was proposed to the Rust Foundation to solve a couple of those issues and to actually vendor in more crates, like for example ZakeDOS or GoDOS. As a second point, I do think Rust testing has a lot of value, even if you're completely using safe Rust, because you can find panics, or you can find error states that you didn't handle, or for example you thought that you're terminating an error at a specific boundary for a user message, but you actually missed some case. So Rust testing is still incredibly powerful.
Yeah, it's a really key point, thanks, that even if your code is 100% safe Rust, fuzz testing is still a very powerful technique, because you can have bugs that are not memory on safety, but are still bugs you'll want to know about. Yeah.
So, just I wanted to say also, really all the NPM issues, etc. That there's a lot more code being pushed by everyone now. That it's in exponential growth, and that's why we cannot trust. We've seen open source projects being hammered with PRs by the OpenClaw or anything that the author doesn't even know. Well, that said, which is, I also have a question. If you had a look at Ban's recent port from Zig to Rust.
I read about it, I haven't looked at it.
Okay.
I understand that they did an entirely AI-driven port of a pretty enormous amount of code.
And some companies are trying to switch away from Ban because they don't trust it anymore, because of this Vibe coded.
Yeah.
Which is a whole runtime for people who don't know Ban, is an alternative runtime to Node.js.
Just also wanted to mention something.
Yeah.
For example, tools like Verifast, I mentioned earlier, uses techniques like separation logic in the formal reasoning.
Okay.
And the separation logic is basically, or the separation logic theory, is basically used to reason about memory-related features. For example, you can write properties on your pointers, and you can reason about the behavior of the pointers, the memory, etc., etc. So these techniques are also quite interesting. And I heard that many people in the audience are repeating, I can't trust, I can't. So yeah, we can trust any code basically. We can trust any code as long as we don't have formal proof, basically, a complete proof saying that that code is completely sound and safe.
Yeah.
So that's why,
Yeah.
yeah.
But we can approach that from a couple of directions. One is if we're the consumer of somebody else's crate, if we've got some good analysis tools, be they static or dynamic, that we wire in as part of our build process, we can get extra insights in case something bad has come along with those crates we picked up. And significantly, tapping into this idea of trust about to become a really important part of software supply chains, inevitably, given things that have happened recently. If you're on the provider side, you've got your cool new Rust project, you put it up on GitHub and you want people to use it, the more things you can do to help make your code trustworthy, the more other people are going to feel comfortable about making it part of their crate dependencies. And if you find yourself in a situation where you say, oh darn, I've got a legitimately good reason why part of this is going to be unsafe, using these sorts of tools we've been looking at can go a long way towards taking you from somebody who threw up a bunch of code on the internet to somebody who has demonstrated they've put the work into evaluating the soundness of their code, which is the question that your consumers should soon be asking themselves. And with that, I know we're running short on time, so I want to say thank you to everybody. Really enjoyed talking with you all. I really appreciated all the discussion and Q&A. I learned new stuff from this, which is awesome. And I want to put out a call to action. There's room for speakers at the next one of these. All of you are doing cool stuff in different areas. So maybe you've got some area where you've been working on it for a long time and you've learned some things through hard-earned experience. Sign up for a tech talk and share it with us. Or maybe you're just getting into some new stuff. You've still got a uniquely valuable perspective as somebody coming to a new technical space with fresh eyes. If it's your first Rust project, you're going to see things that somebody who's been working on Rust for 10 years might overlook, and you'll have some valuable insights. So we want to put out the call to all of you. Sign up for a tech talk, talk about the stuff that you've been doing, and share with the rest of us. With that, thanks so much. And finally, I want to thank Barry and his crew here at tcube, because it's not easy to do the logistics of putting on a tech talk. He had to do a lot of work behind the scenes, a lot of heavy lifting, so I could stand up here and talk about Rust. And so I wanted to express my gratitude to you.
Thank you.